Let me show you something before we start. A company runs an A/B test. The new button gets a 3% higher click rate. The p-value is 0.04. The team ships it. Everyone celebrates. And 6 months later, nothing has changed. Revenue is flat. So what went wrong? Nothing. Technically, the maths was correct. The problem is that almost nobody in that room actually understood what that p-value was telling them. And that is the thing about statistics. You don't get punished for not knowing it. You get punished for thinking you know it. Here's what I've noticed. Most analysts can calculate. Very few can tell you when a number is lying to them. So this crash course is built differently. We're not going to derive formulas. You have a computer for that. We're going to build the intuition that stops you being fooled. Averages that hide the truth. Distributions, sampling, confidence intervals. What a p-value actually means in plain English. A/B testing, correlation and causation, regression, and the traps that catch smart people. This is the one that separates analysts who get promoted from analysts who just produce charts. First, let me frame the whole subject. Because statistics feels enormous, and it really isn't. Statistics does exactly 2 jobs. Job 1. Describe what you have. You've got 1,000 customer orders. What's typical? How spread out are they? What's the shape? That's descriptive statistics. It's just summarizing. No guessing involved. Job 2. Guess about what you don't have. You surveyed 500 customers out of 50,000. What can you say about all 50,000? That's inferential statistics. And that's where everything interesting and everything dangerous lives. Because the moment you generalize from a sample to a population, you're making a leap. And statistics is the toolkit for measuring how risky that leap is. That's it. Describe and infer. Every technique you'll ever learn sits in one of those 2 buckets. And here's the analyst framing that matters. You are almost never asked, what is the average? You are asked, is this real or is this noise? Did the number actually move or did we get lucky? That question is what statistics answers. Right. Descriptive statistics. Measures of center. 3 of them. The mean, which is the average, the median, the middle value when you sort them, and the mode, the most common value. Now here's the important part. Not which one to calculate. When each one lies. The mean gets destroyed by outliers. Classic example. 9 people in a room earning about 50,000. Then a billionaire walks in. The average income in that room is now over 100 million. Technically correct? Completely useless. The median barely moves because it just asks who's in the middle. So the rule, if your data is skewed, and money data almost always is, report the median. Salary, house prices, customer spend, order value, all skewed. All should be median. And here's the analyst move that gets you noticed. When someone hands you an average, ask for the median too. If they're far apart, you've got skew, and the average is hiding something. That one question makes you look sharper than half the room. Now spread. And this is the part people skip, and it's genuinely more important than the average. 2 teams both average 50 sales a month. Team A does 48, 51, 49, 52. Team B does 5, 90, 12, 93. Same mean, completely different reality. One of them you can plan around. The other is chaos. That difference is spread. 3 ways to measure it. Range, the max minus the min. Simple, but one outlier ruins it. Standard deviation, the typical distance from the mean. This is the one you'll use most. Small standard deviation means everything clusters near the average. Large means it's scattered. And interquartile range, or IQR, the middle 50% of your data. Sort everything, chop off the bottom quarter and the top quarter, and see how wide what's left is. IQR is the robust one. Outliers don't affect it. So if your data is skewed, use median and IQR together. If it's roughly symmetric, use mean and standard deviation. And never ever report an average without some measure of spread beside it. A number without its spread is half a number. Let's talk about distributions. Because the shape of your data changes, which tools are even valid? The normal distribution, the bell curve. Symmetric, most values near the middle, tails thinning out on both sides. Heights, measurement errors, lots of natural things. And there's a rule worth memorizing. The 68, 95, 99.7 rule. About 68% of the data falls within one standard deviation of the mean, 95% within 2, and 99.7% within 3. So if something is more than 3 standard deviations out, that's genuinely unusual. Then skewed distributions. Right skewed, which means a long tail to the right, is what most business data looks like. Income, purchase value, time on site. A few very large values dragging the mean upward. And the practical point. A lot of classical statistics assumes roughly normal data. If your data is heavily skewed and you apply those tools blindly, your conclusions can be wrong. So before any test, plot a histogram. Just look at it. 30 seconds of looking prevents a lot of embarrassment. Now, inference. And this is where it gets genuinely useful. You almost never have all the data. You have a sample. And the entire question is, how much can I trust what this sample tells me about everyone? Two things matter enormously. First, sample size. Bigger samples give more reliable estimates, but with diminishing returns. Going from 50 to 500 helps a lot. Going from 50,000 to 100,000 barely helps at all. Second, and this is the one people get wrong, how the sample was selected. A biased sample of 1 million people is worse than a random sample of 1,000. Here's the classic example. 1936 US election. A magazine polled 2.4 million people. Enormous sample. They predicted the wrong winner badly. Why? They sampled from car registrations and telephone directories in the middle of the Great Depression. So they only reached wealthier people. Size didn't save them because the sample was skewed from the start. So whenever someone shows you survey results, ask one question. Who could not have ended up in this sample? That's usually where the problem is. Now the single most important idea in statistics, the central limit theorem. And I'm going to explain it without any maths. Here's the idea. Take a sample, calculate its average. Do it again with a different sample. And again, and again. Now plot all those averages. Here's the remarkable part. Those averages form a normal distribution, a bell curve. Even if the original data was not normal at all, even if it was heavily skewed, the averages still come out bell-shaped. Why does that matter so much? Because it means we can use all the well-understood maths of the normal distribution on almost any kind of data, as long as we are working with averages and the sample isn't tiny. This is the foundation. Confidence intervals rest on it. Hypothesis tests rest on it. A/B testing rests on it. And there's one practical thing that falls out of it. The standard error. That's just the standard deviation of those sample averages. It tells you how much your estimate would wobble if you repeated the study. And it shrinks as your sample grows, which is exactly why bigger samples give you tighter answers. Confidence intervals. And these are far more useful than most analysts realize. A single number is a guess. A confidence interval is a guess with honesty attached. Instead of saying average order value is 1200 rupees, you say average order value is between 1150 and 1250 with 95% confidence. Now what does 95% confidence actually mean? Here's the correct interpretation. If you repeated this study 100 times, about 95 of those intervals would contain the true value. It is a statement about the method over the long run. What it does not mean is that there's a 95% probability the true value is inside this particular interval. That sounds almost identical. It isn't, and that distinction gets asked in interviews. 3 practical things. Wider interval means more uncertainty. Bigger sample makes it narrower, and higher confidence, 99 instead of 95, makes it wider. There's a genuine trade-off between being confident and being precise. And the analyst habit. Always report the interval. A number alone hides how much you actually know. Hypothesis testing. This is where most people memorize steps without understanding what's happening. So let me reframe it. Hypothesis testing is a courtroom. The null hypothesis is the defendant, and it's presumed innocent. The null always says, nothing is happening. There's no difference. The new button is exactly as good as the old one. The alternative hypothesis is the prosecution's claim. Something is happening. There is a difference. Now here's the crucial part. You never prove the null true. Just like a court doesn't prove innocence. You either find enough evidence to reject it or you don't. Not guilty is not the same as innocent. And that maps directly onto statistics. Failing to find a significant difference does not mean there is no difference. It might mean your sample was too small to detect one. This is why we did not find a significant effect and there is no effect are two completely different statements. Analysts who confuse those two make bad recommendations. So the whole game is, Assume nothing is happening. Then ask, how surprising is my data if that assumption were true? Which brings us to the p-value, the most misunderstood number in all of business. Here is what a p-value actually is. It's the probability of seeing a result at least as extreme as yours, assuming the null hypothesis is true. Read that again, because every word matters. Assuming nothing is really happening, how likely was my data? A small p-value means my data would be surprising if nothing were going on. So maybe something is going on. That's all it says. Now, what a p-value is not. It is not the probability that your hypothesis is true. It is not the probability that the result happened by chance. And it absolutely is not a measure of how big or important the effect is. That last one causes real damage. With a large enough sample, a completely trivial difference becomes statistically significant. 0.1% improvement, p-value 0.01, statistically significant. Commercially, meaningless. And the 0.05 threshold? It's a convention. Ronald Fisher suggested it. It is not a law of nature. A p-value of 0.049 and 0.051 are essentially the same evidence. So, if the p-value doesn't tell you if something matters, what does? Effect size. This is the number that answers how big is the difference. And it's the one that should drive your decision. P-value tells you, is it probably real? Effect size tells you, do we care? You need both. A real but tiny effect is not worth a launch. A large effect with weak evidence needs more data. Always report them together. Then, statistical power. Power is the probability your test detects a real effect if one exists. Standard target is 80%. Low power is a quiet disaster because an underpowered test finds nothing and everyone concludes there's no effect when actually the test was never capable of finding it. And this is why you calculate sample size before you run the test, not after. You decide the smallest effect worth detecting and work out how many observations you need. Running a test first and then wondering why it was inconclusive is the most common waste of time in analytics. A/B testing. This is where all of it becomes practical because it's the statistics most analysts actually run. The process. 1. Define your metric first before you look at any data. Conversion rate, revenue per user, whatever it is. Decide now. 2. Calculate the sample size you need based on the smallest effect that would actually matter to the business. 3. Randomly assign users. Randomization is what makes the comparison fair because it balances out everything you didn't think to control for. 4. Run it for a full number of weeks, not 5 days, because Tuesday behaves differently from Saturday. And if you stop midweek, you've built a bias into your result. 5. Analyze it once, at the end. And that brings us to the biggest sin in A/B testing. Peaking. Checking your results every day and stopping the moment you see significance. This dramatically inflates your false positive rate. If you check 20 times, you will almost certainly hit P less than 0.05 at some point, purely by chance. Decide the duration up front, then wait. Related to peaking, and just as dangerous, multiple comparisons. Here's the intuition. If you test 20 different things at a 5% significance level, you'd expect about one of them to look significant, purely by chance, even if nothing is real. So if you run an A/B test and then slice the results by 20 segments, looking for anything that pops, you will find something, and it will probably be noise. This has a name, p-hacking, and most of the time it isn't deliberate fraud. It's just an analyst under pressure slicing until something looks interesting. The fixes. Decide your primary metric before you start. Anything you discover afterwards is a hypothesis for the next test, not a conclusion from this one. And if you genuinely need to test many things, apply a correction, like Bonferroni, which tightens the threshold based on how many tests you ran. Here's the mindset that protects you. Exploratory analysis generates questions. Confirmatory analysis answers them. Do not confuse the two, and never present an exploratory finding as though it were a confirmed result. Correlation. It measures how two variables move together on a scale from -1 to +1. +1, perfect positive. -1, perfect negative. 0, no linear relationship. 3 things to know. First, and everyone says it but few internalize it, correlation does not imply causation. Ice cream sales correlate with drownings. Ice cream doesn't cause drowning. Summer causes both. That third factor is called a confounder, and hunting for confounders is a large part of good analysis. Second, correlation only measures linear relationships. You can have a perfect curved relationship, a clear pattern, and a correlation near zero, which is why you must always plot it. Third, and this is the underrated one, correlation is extremely sensitive to outliers. One extreme point can create a strong correlation out of nothing or destroy a real one. So the rule, never trust a correlation coefficient you haven't seen a scatter plot of. Look at Anscombe's quartet sometime. 4 datasets, identical correlation, wildly different shapes. It takes 30 seconds and it will stay with you. Regression. And you need less of this than you think, but the intuition matters. Simple linear regression fits a straight line through your data, and that line lets you say something genuinely useful. For every 1 unit increase in X, Y changes by this much, on average. That coefficient is the interesting part. If you regress revenue on marketing spend and the coefficient is 3, that means every extra rupee of spend is associated with 3 rupees of revenue. Note the word associated, not caused. Then R squared. It tells you what proportion of the variation in Y your model explains. R squared of 0.7 means 70% explained. But do not chase a high R squared. It is not a goodness score. You can inflate it by adding meaningless variables. And a low R squared can still be a genuinely useful model if the relationship is real. Multiple regression adds more variables. And here's why it matters. It lets you say, holding everything else constant, what does this one variable do? That's how you start controlling for confounders, which is how you move from describing to actually explaining. Now let me show you the trap that catches genuinely smart people. Simpson's paradox. A trend appears in several groups, and then it reverses when you combine them. Real example. A university is accused of bias because overall it admits a lower percentage of women. But look department by department, and most departments admit women at a higher rate. Both statements are true. How? Women were applying in larger numbers to the most competitive departments, which have low admission rates for everyone. The aggregate hides that. So the aggregate says one thing, the breakdown says the opposite. And here's why this should genuinely worry you. Every dashboard you build shows aggregates. Every one of them could be hiding a reversal like this. The defense is a habit. Whenever you see a headline number, ask, what happens if I break this down by the obvious segments? Region, time period, customer type. If the story flips, you've just found the actual insight. This is the single highest value question an analyst can ask about their own work. 3 more traps, quickly, and they all cause real damage. Survivorship bias. You only see the things that made it. The classic example is from the Second World War. Analysts examined returning aircraft, saw where the bullet holes were, and proposed armoring those areas. Abraham Wald pointed out the flaw. Those are the planes that came back. Armor the places with no holes, because planes hit there didn't return. In business, this is studying successful startups to learn success. You're not seeing the failures who did exactly the same things. Regression to the mean. Extreme results tend to be followed by more ordinary ones. Your best salesperson this quarter will probably do worse next quarter. Not because anything changed, just because extremes are partly luck and luck doesn't repeat. This is why we coach the worst performers and the improved is almost never evidence the coaching worked. And selection bias. Your data was collected in a way that excludes part of the population. Survey responses only come from people willing to respond. That's a different group from everyone. AI and statistics. And this is a genuinely interesting case because AI is both very good and very dangerous here. What it's excellent at, explaining concepts with a worked example using your actual numbers. This is honestly the best statistics tutor that has ever existed. And it's free. If you don't understand why your p-value doesn't mean what you thought, ask it, and ask it to walk through a concrete example. Second, choosing a test. Describe your data and your question, and it'll suggest whether you want a t-test, a chi-squared, or something else. Verify it, but it's a good starting point. Third, writing the code, in Python or R. Fourth, sanity checking your interpretation. Paste your result and ask, what am I concluding here that the data doesn't actually support? Now the danger. AI will produce a confident, fluent, statistically wrong interpretation, and it will sound authoritative. It doesn't know your data was collected badly. It doesn't know you ran 12 tests before this one. So the rule stands. Use it to learn and to check, never to outsource the judgment. Before we wrap, here's the checklist I'd actually run before presenting any statistical result. 1. Did I plot it? Not just calculate it. Actually look at the distribution and the scatter plot. 2. Is my sample representative? Who could not have ended up in this data? 3. Am I reporting spread, not just a center? 4. Is my effect size meaningful to the business, not just statistically significant? 5. How many things did I test before finding this? Be honest with yourself. 6. What happens if I break this down by an obvious segment? Does the story hold? 7. What's the most plausible alternative explanation? A confounder, selection bias, regression to the mean? And 8. Can I state my conclusion in one sentence a non-technical person would understand, without overstating it? That last one is the real test. Because if you have to hide behind jargon, you probably haven't understood it well enough yourself. Run that checklist and you'll be more careful than most analysts I've worked with. So how do you actually learn this? Here's the order that works. Week 1, descriptive statistics. Mean, median, sprod, distributions. Plot everything. Week 2, sampling and the central limit theorem. Get the intuition. Skip the proof. Week 3, confidence intervals. Practice interpreting them out loud, in plain English. Week 4, hypothesis testing and p-values. This is the week that matters most. Week 5, A-B testing, end-to-end. Sample size, run, analyze. Week 6, correlation and regression. Week 7, the traps. Simpson's paradox, survivorship bias, p-hacking. Then, ongoing. Apply it to real data and write up your reasoning. And your portfolio move. Take a public dataset. Ask one real question. Run the analysis and write a page that includes explicitly what you cannot conclude and why. That last section, the limitations, will impress a hiring manager more than any model. Quick recap. Statistics does 2 jobs. Describe and infer. Averages lie when data is skewed. Always report spread. A p-value is not the probability you're right. Effect size is what matters. Correlation is not causation. And always break down the aggregate. If this helped, subscribe. And tell me in the comments which statistical idea took you longest to genuinely understand. See you in the next one.